In this video, we're going to talk about modeling exponential growth and decay with an equation. Last time we were doing it primarily in Excel, or maybe exclusively in Excel, and now we're going to look at an approach that you maybe see more in a traditional, like college algebra, or I think we even touch on this a little bit in our intermediate algebra course here at ECC. So suppose that we first just kind of consider what we were looking at last time. So here's our table of values, and we did observe last time that anytime you have a quantity increasing or decreasing by a percent, R%, then we can think of that as exponential growth or decay, because each time as we go from one x value to the next x value and so on, okay, every time we do that, we are multiplying by a factor of either 1 plus r if we have growth, or 1 minus r if we have decay. So every single time we're multiplying by either 1 plus or minus r, and that's really our growth or decay factor. So this is what we looked at last time. So if we were to think about representing this as an equation, some of these pieces hopefully will, you'll be able to make the connection between what we saw in the spreadsheet as well. So we're going to look at two basic ways that you can express this exponential equation. One is to think of it as y equals a times b to the x. The other is replacing the b with the 1 plus or minus r. So let's break down each of the pieces here. So first of all, the A. So the A quantity is the initial value. Well, that's too much there. You don't want to draw over it. Sorry. All right, so let's try this again. All right, so this A value, so this is, oh, it's still the same thickness, but this is our initial value. And so at time equals 0 or whatever the initial condition is. Now the B is if they give you the growth or decay factor, then that's what the B is going to compute to be. So the B is your growth or decay factor. Now, many times they may not give you the growth or decay factor. So for example, if something's doubling, the growth factor would be 2. If something was being cut in half, then the decay factor would be 1/2. Now, if that's not given, often instead what we are given is a way to come up with B, just like we saw last time in Excel. This growth or decay factor, if described as percent change, can come from looking at 1 plus or minus r. So here is where that value of r is going to come in. So r is going to be that percent change, that percent increase or decrease, but make sure you put it in its decimal form first. So we want to just kind of be cautious about that. So those are the constants that we are going to fill in for these specified variables. And then really what we have is the output variable is y, and the input or the independent variable is x. So everything else here is constants. All right, now the one thing that we want to think about is just being a little bit careful that if you do have a situation that is growth, so for exponential growth, make sure you're using addition, so 1 plus r, and then that will result in B, the growth factor, being larger than 1. And then if you have decay, then decay is going to be subtraction, 1 minus r. And then that 1 minus r will give you a value in between 0 and 1. X will again be your input or your independent variable, and that'll be in terms of time. whatever the unit of time is being described as in the rate. Like if you're talking about an annual growth rate, then X would be time in years, for example. So let's take a look at an example that we did last time, but we did it in Excel. We set up a spreadsheet. All right, so now we're going to do it, but we're going to do it with an equation. So let's keep my equation displayed here at the top. Alrighty, so the U.S. population was growing by about 0.8% each year. In 2000, the population was 282 million. We're going to write out the exponential model as an equation here. So we have our y, there's our output, equals. All right, so the A is this 282. So that is the initial quantity. So this right here, that is our value of A, the initial quantity. Now, they didn't describe a growth factor like the population is doubling or growing by a factor of 2.38 or anything like that. So instead, they described it as a percent increase. So this is where they've given us not the B, but they've given us the R, and that is certainly going to be enough to allow us to determine what the B is. So just being careful that if we have growth by 0.8%, then our R, when we fill it into the equation, is going to be 0.008 as we move our decimal 2 places to the left. So this is the R. Another observation to make here is this was growth. So when we have growth, that is where we have the 1 plus. So that's why we have addition. So then rewriting this, we end up with our y equals, again, the A, it's the 282, the initial quantity. So here time equals 0 is going to correspond to the year 2000. When you actually add the 1 plus the 0.008, this actually gives us then what the R is. I'm sorry, the B is. So the 1 plus the R is what gives us the B. So if you had to, let's say in your homework, enter this in the form of A, B to the X, or A, sometimes there's different uses of variables for the base. I've used B here, sometimes they use a different variable, but that growth factor is now the 1.008. And again, the X is the independent or the input variable, and that will be our time in years after the year 2000. All right, so for the question here, for the year 2050, that would mean X is equal to 50, because this is the number of years after the year 2000, and then we would just be subbing 50 into this equation. And so we would end up with approximately 420, you can see the decimal there is million, because everything, the initial value is in millions, or you could expand by moving your decimal 6 places there to the right. All right, let's look at another example. Suppose a drug breaks down in the body. So first of all, as we look at this one, we just want to observe that this breaking down portion here, that is going to tell us that we have subtraction. So right here, the breaking down, that is what is going to tell us that we're going to be using the subtraction here. And so it's breaking down at a rate of, so here's my 17%, which when we get ready to put into the equation, we're going to want to think of that as 0.17. It's supposed to be an equal sign, sorry. The initial quantity, all right, great. So this is my value here for A. So A is equal to 10. And so we have everything we need for our model. So we have Y equals, here's my A. So this is, again, our value of A, and then we have times the quantity of our 1 minus R raised to the X power. So there's where we're filling in the R and the A. Again, when we do the computation of the 1 minus the 0.17, that gives us the 0.83. So we have Y equals 10 times 0.83 to the X. So that's our kind of completed A, B to the X form. And so now if we wanted to determine how much there would be when x is equal to 5, we are simply subbing 5 into our equation for x. And so in this case, let's go ahead. I opened up an online calculator here. So we were entering in, we had an A that was 10, and then we were multiplying that times our B was this 0.83, and that was raised to the, so where's my caret here? I've never used this one. So, oh, there it is, A to the B power. So this one doesn't have a caret. There's my exponent. So 0.83 raised to the, and in this case, what was I raising to? The fifth power. So here's what I have, 3.939. So let's go ahead and go back. So this would have ended up being 3.939 milligrams. Of course, we could have set this up with Excel. That's what we did last time. So these are kind of the two different ways we could have modeled that in Excel, and you would get the same thing. One of the first questions that you're going to have on your next group activity is going to be, as a matter of fact, let me jump ahead to that. You're going to have to do kind of both representations. So here you're going to be setting up your equation, you're going to make a prediction, and then I'm going to have you go back and set up your spreadsheet and confirm that you get the same thing that you do with the equation. So that's an important thing to observe. So, you know, doing it with the model and then doing it how we did last time, like this. So this is what you want to refer back to, kind of these two pieces here when you're looking at that question in your group activity. All right, let's take a look at one more here. So we had this last time, so we start off and we take a shot of espresso and we are going to initially ingest 64 milligrams of caffeine, and it's being eliminated from the body at a rate of 11.5% per hour. All right, so let's take a look here. And so initially, of course, we have our y equals, and we're looking at our a times the b to the x, where again the b is going to come from 1, and in this case, because it's being eliminated, it's going to be minus r raised to the x power. So that's the equation that we're working with. So let's see if we can kind of look at some of these quantities that we have. So we initially ingest this 64 milligrams of caffeine. So this is my value here for A, and it's being eliminated. So that's how we knew in this problem that we were going to be dealing with the subtraction, the 1 minus R. And it's being eliminated at a rate of 11.5% per hour. So this is going to tell me that my R in this case is going to be in decimal form. It's going to be 0.115 as a decimal. So this is going to be my value here for the R. So let's just kind of continue. Let's write this out. So this is still all equal to y here. So the initial value, A, is our 64 times the quantity of 1, and then minus, because it's being eliminated, r in decimal form, 0.115 raised to the x power. So here's what our completed model looks like. So we have our y equals the 64, and then if you actually do your 1 minus 0.115, you're going to end up with your 0.885 raised to the x power. All right, so now that we have this completed model, we want to use it to answer the question. So this question is, how much caffeine would be left in our body at 10 p.m.? So 10 p.m. is 8 hours after the initial quantity, which was the 64, was ingested, and that was at 2 p.m. So this means we're going to be subbing in that 8 for x. So we're going to have our 64 here times our, oops, I didn't mean to actually erase all of that. Y equals our 64 times 0.885. So I ordered a stylus, so I'm hoping to have neater looking notes that I do here. Right now I'm going back and forth between using my finger on the touch screen and then using the mouse. So I apologize for the poor penmanship. Not that I have great penmanship to begin with, but all right. And so we said we were looking for subbing in at 10 p.m. So 10 p.m. we said that was going to be 8 hours later. So we are subbing in 8 for x. All right, so let's see what we would end up with here. So we're going to end up with, and we'll go to that online calculator here. So y is going to equal, so 64, where is it in here? Yeah, okay. So let's clear that. So we had 64, and that was being multiplied by 0.885, which was raised to the, and it was 8 hours later. And so that was 24.08 approximately. So let's go back here. So we would have had approximately 24.08 milligrams. So that is the amount of caffeine that would be in our body at 10 p.m. So again, this was one that we did with Excel before, so you're welcome and should go back and kind of do some side-by-side comparing there. So then what we're going to start to get into on the next video, we'll get into using some Excel again. We're going to get into two concepts of doubling time and half-life, which are kind of intuitive concepts. Doubling time is the amount of time it takes something to double, a population or whatever it is that we're looking at. So the amount of time to multiply by 2 is the same thing to grow by 100%, just another way to phrase that. Half-life then is the amount of time it takes the population to be cut in half. So you could also say that it's declining by 50%. So we're going to primarily use Excel to solve those, if not entirely Excel to solve those. So that's what we're going to take a look at in the next video.